welcome back. So we were talking about maximum likelihood estimation. So the idea is this: I know corresponding to a particular localization of the mean of the standard normal distribution, there is a peak somewhere, right? And when you reach the peak, and please note this, when you reach the peak, that's where the tangent line becomes parallel to the horizontal axis, okay? And you know the implication of that, the derivative will go to 0, right? We'll come back to that later on. So the idea is, from a bunch of numbers, from a bunch of measurements which lie on the horizontal line, you're actually projecting it up. You're projecting it up in such a way that you are able to generalize the mean and the standard deviation, or you're able to localize the mean and the standard deviation to the peak of the curve, right? So that's the whole idea. So to summarize, the framework is like this: we have the MLE estimates for the mean. Let's say we have the MLE estimates for the mean, okay, all right. And what we also have is that we found the value. So we found the value for both mean and standard deviation, right? So these two are equivalent, and you combine these two, and what you obtain is, what MLE does is MLE tries to find what is the process of MLE is nothing but finds optimal mu and sigma, okay, for a distribution given a bunch of measurements, okay. So roughly this is the framework of maximum likelihood estimation, okay. So what we are trying to do, let's write in, we locate mu, okay, and we also try to locate sigma. Alright, now what we know about this is a location of mu. How does it matter? If you have like a smaller mean value, what will happen is it will move the distribution to the left. If you have a larger mean value, it will move the distribution to the right, okay. About the standard deviation actually determines the width of your density function. So if you have a large standard deviation, it's like a fat density function, okay, it's like a bond, right? However, if it has a small or smaller value of the standard deviation, what we will get, you will get a sort of a really skinny density function. Both are normal though, okay, but the width changes, okay. So let's now do some overlay with a normal distribution with a bunch of data that we sort of make up. Let's just make up some data, okay. All right, so let's proceed to just do a sort of data exploration, okay. So we are still continuing. Okay, so let's say we have some measurements, and there is this 24 kg, right? There is this 40 kg. These are the range of weights. There are a bunch of measurements that we have, and somewhere in between the average value is 32 kg. Okay, right. So what we know is that the idea is this. Idea is that I have a likelihood function. So this is just a Bayesian notation, okay, all right. So the d for data and theta are the parameters. These parameters are, in your case, the mu and sigma, okay. And this is sort of, I'm going to use an equivalent notation, which is, okay, all right. And we know that this is because it's a univariate Gaussian. We know how this looks like, right? We are going to use this, okay, all right. Now, so I have the data, right? So I have the form of the density function, and I have the data now. So I can, given some value of the mean and some value of the standard deviation function, I can just plug in those numbers. Okay. So let's take some data. Let's take a single measurement of the weight. Okay. And let's just, some standard data. So let's say the average is 28 and the standard deviation is 2. Okay. All right. So what we are trying to do, we are going to overlay the normal density function. So this is a normal density function onto the data. So overlay this onto our measurements or whatever measurements we have. Okay. Now it's sort of easy, right? I mean, because your a particular data point, which is we know that this is 32, right? The particular data is 32, and what you are trying to do, you are trying to fit this particular data into a standard normal density function with mean 28 and standard deviation 2. So you plug in x is equal to 32 here, and you plug in mu is equal to 28, and your sigma is 2, and you do the simplification. What you will find is that, I'm not going to skip the calculation, I'm going to find that this is 0.03. Okay. Now, what is this? This is the likelihood. Okay. This is likelihood that a single measurement is captured by this density function. Okay. Which is 0.03. Not bad. Okay. However, let's shift the mean of this particular density function slightly to the right. So we are now, we'll consider, we will keep the standard deviation constant. We are not going to change it, but we'll change this guy to 30. Okay. All right. And recompute this, recompute the likelihood. All right. So if you recompute the likelihood, so let's call this L. Okay. The likelihood. So let's recompute the likelihood. What we will find is just plug in mu is equal to 30, everything else remains constant. You will actually find that the likelihood has increased from 0.03 to 0.12. So this is better, right? So given the measurements that we have, and we are trying a bunch of different standard normal functions, a standard normal function with mu 30, mean 30 and standard deviation 2 fits this data better. Okay. So there is, the likelihood of fitting the data is much more compared to the likelihood of fitting the data with the previous density function. Okay. All right. So this whole thing boils down to identifying the peak. Okay. So once again, like it or not, we have to revisit to actually know what is the maximum likelihood estimate of the mean and the standard deviation for the standard normal density function. And you will find it surprisingly that it's like, it's where you would expect it to be. Okay. All right. Okay. So, we cannot do both likelihood estimations simultaneously. When you do the maximum likelihood estimation for the mean, you keep the standard deviation constant. And when you do it for the standard deviation, you keep the mean constant. Okay. All right. Now, this is like a single measurement. We observe the data once. What happens if we observe, like you have two instances of the observed measurement. So, let's say we have something like x1 equal to 32 and x2 equal to 34, right? Two measurements. So your likelihood function, the way you should write it is the following manner, right? I'm using this same density function, which is mu equal to 28 and sigma equal to 2. Given that, I now have two instances. Okay. So what do I do? So this is my likelihood function, right? So I am going to make an assumption, and this assumption is IID. What is IID? It's identical, independent and identically distributed. Okay. So what I'm assuming is that every observation that I make are identically distributed. So if one is Gaussian, the other one is also Gaussian, and so on and so forth. In this way, I can have a bunch of Gaussians, okay, identically distributed, and they are independent of each other. So observations do not depend on, there is no dependency between the observations. So if that's the case, then what I can do is I can compute the likelihood of each instance individually and just take the product of the two. Okay. So this is an assumption that I'm going to make. Okay. All right. So moving on. So what this means is, I start from one observation, a single measurement, and then keep adding data points. So my data set now, the D guy, is x1, x2, all the way up to xn. And therefore, by virtue of the likelihood function, what I'll do is I'll take the, since I know that I can take the product, so I'll take the product of all such data points. Okay. So what is the MLE estimation then? The MLE estimation is, there is as I said, we have to revisit calculus. There is a derivative with respect to mu and there is a derivative with respect to sigma, and we have to do this calculation separately. Okay. So when we do this for mu, we keep the sigma constant. When we do this for sigma, we keep the mu constant. Okay. All right. Okay. So let's go ahead and do that. Okay. All right. So of course, I mean, instead of computing the likelihood, we tend to compute the log likelihood, because the logarithmic function is monotone, and if the maximum of a likelihood function is equivalent to maximum of the logarithm of the likelihood function. So instead of just taking the likelihood, we take the log likelihood. So what we do is we take the log likelihood. Okay. And this is nothing but ln. Okay. All right. Now, what will happen is, because it's a log and the product, right? I mean, there is a nice property of logarithms, so that product can be split into sums. So I'll have a bunch of logarithms. If I write it this way, I mean, I can write it as 1 over square root of 2 pi sigma square e to the power minus x1 means mu square by 2 sigma square, blah blah blah, right? Okay. And then what you do is, I mean, you can further simplify this, because what is happening now is that you have a logarithm in the exponential and then you have something constant, right? So log and exponential are inverses of each other. So what will happen is, I'll have this thing and just minus, so this is just, it's a minus and there will be a minus as well, x1 minus mu square by 2 sigma square and blah blah blah, and this will continue, right? Okay, sorry, this will be ln of this. Okay, so then if I continue, what will happen is, I'll have minus 1/2 ln of 2 pi, okay, minus 1/2 ln of sigma square, which is 2 ln of sigma, right? Okay, minus x1 minus mu square over 2 sigma square. This is only the first term. Okay, all right. And then I have, so I'll just write it together, and everything else is sort of a replica except for the fact that the last term will change. So in the second parenthesis, you will replace this x1 with x2 and so on and so forth. Okay. So when I combine all that, okay, what we'll have is, how many observations do I have? I have I is equal to 1 to n number of observations, right? So combining, if I combine, my log likelihood function is actually nothing but minus n by 2 ln of 2 pi minus n ln of sigma minus, you have a bunch of this, right? Okay, so summation I equal to 1 to n xi minus mu square over 2 sigma square. Okay, all right. Now this is my log likelihood expression. I mean, and I'll take the derivative with respect to mu now. I take the derivative with respect to sigma. Okay, whatever. I mean, I'm going to, and this part is simple, right? So I'm going to skip this. I'll just write this down. So when you are doing an MLE estimation for mu, this is equivalent to del L del mu equal to 0. Okay. So in other words, if I do this, I mean it's easy to see because the first two terms will go away, right? The first two terms will go away and you will have a 2 and 2 cancels out, and then a 2 times xi minus mu, sum of all that, right? Okay. So what will happen is this is going to be summation I equal to 1 to n, and you will just have xi minus mu, right? Okay, equal to 0. Simple. Okay. And since mu is a constant and you have n iterations of that, so basically what you are doing is, it's easy to see that this is what you expect, right? I mean, so when you look at mu, when you look at the maximum likelihood estimation of mu, you will see that it is averaged in the middle, right? So this is nothing but the average of all the observations that we have over n observations, right? Similarly, when we do that MLE for sigma, this is nothing but del L del sigma equal to 0. I am going to skip the intermediate calculus, and what I will find is, if I do this correctly, okay, I will find that I will have I equal to n xi. So what is this? This is sample variance, right? And what is this? This is sample mean, right? Okay. All right. So this is what a maximum likelihood estimation is. Okay. However, I mean, so the point is, I mean, when do I do a maximum likelihood estimation? The thing is, if you have a lot of data and your experience does not really count on including prior. I mean there is some prior data that you may use. However, this is like, I can keep adding observations, and I am also assuming I have enough number of observations to do the estimation. So I mean, you do this when you have a lot of data and you have no dearth of data. However, if you don't have lot of data, I mean, then you would probably need to include a prior. Okay. All right. So perhaps, okay. And so this will give rise to something which is what is known as MAP, or maximum a posteriori estimation. This is also a point estimate, mind it, right? But however, it has the additional advantage that it includes a prior to your data distribution. Okay. With this, let's move on to in the direction of map from MLE, and let's see how we traverse this journey. So the idea of maximum a posteriori estimation is this: given there is data sampled from real space, real Euclidean space, we assume a joint distribution. Now theta is a random variable. I hope you know what a random variable is. It's nothing but a actually it's a function that maps to real numbers. Okay, the goal is to choose a good parameter theta. So this theta, we can interpret this theta as a hypothesis. Okay, so I mean, if you want to use maximum likelihood estimation in a classification problem, then if you choose a good theta for your data, I mean it will amount to correct prediction of classes. Okay. All right. So what's the key difference? In the estimation part, I mean, when you are estimating the mean, right? Let's say, for example, I mean, you would have a prior information about the mean. Okay. So you know that, okay, look, in the historical data, so the one big difference from MAP, I mean, between MAP and MLE is that, there is this advantage of having some historical data. So historical data means if you have historical data, you would also have information about the historical averages, historical sample averages, right? Okay, so use that in the estimation itself. So it's slightly different from the MLE calculations, but not too much. Okay, all right. So the idea is, even if this is the problem statement, then you have two types of estimation that you can do on your parameter. One is you can do a maximum a posteriori estimation, which is nothing but taking the maximum of the likelihood, right? So this is nothing but, I mean, if you think about it, from a Bayesian point of view, this is nothing but the posterior density. And so there is this MLE on theta, which is nothing but, so please notice the difference. This is just the likelihood function, right? And how are these two related? So you can think of this as, isn't it? I mean, if you think of this, it is nothing but, so it's like a Bayesian interpretation, right? I mean, you compute the posterior, okay, by using the likelihood and the prior together. What we are doing earlier was that we are just considering this part, the likelihood itself, not the prior, right? So this is nothing but the prior, right? Okay, all right. So this part is the MLE part. So what we can see easily, at least from a high level abstract point, is that a map estimation is sort of an extrapolation from MLE. Okay, so I can write a note here, map is an, okay, all right. Now if you have prior data, of course, so I mean it will help you, avoid the problem of overfitting. Why? Because I mean if you don't have prior data, you are trying to fit data as they come. So I mean you really have no way to anticipate variances in your validation data set, right? Because I mean the data comes is a sort of an online, and you are not able to use the prior information to know something about the general trend of the data, okay, including the variance. Okay, it's also easy to compute, it's not hard, right? However, I mean just like MLE, it's a point estimate. So therefore if it's a point estimate, there is no representation of uncertainty. Okay, and also you have to, if you don't have prior data, much prior data, and you still want to use map maximum a posteriori, then you have to assume some prior distribution on the theta as well. Okay, so it's like, I mean if I take a small example, I mean if I have something like this, right, and if you do a map on this, obviously because it's a maximum a posteriori, map will say that this is where your parameters are maximized, right? Okay, so map will say that maximized here, but that's not true. It's not true, right? Because why? Because most of your data is here. Most of your data is here. Okay, so therefore from a representation point of view, it's not really correct. So I mean, so what you see here is a sort of an uncertainty and a noise, a sort of an randomness in your data that is actually pushing you away from taking a reasonably good decision regarding where your parameters are. So this is one of the problems of maximum a posteriori estimation. Okay, so we will continue this in the next lecture, where we first show the parameter estimates by using map, and then also continue to discuss the relationship between maximum likelihood estimation and maximum a posteriori. Okay.